Okay. Everybody sees the screen? I can check the schedule. If anything, if it clashes, um, our post an announcement and we can find a different time, or I can just record a tutorial and you guys can sort of look through that, right? Yeah. And then for next week, there's not going to be a tutorial just because Thanksgiving is on Monday. So the Monday session, since they're not going to have a tutorial, it was decided that the rest of the groups won't have a tutorial. They're going to be sending out sort of like a self-prep tutorial for next week. So the head TA is going to sort of put together like sort of a handout that you're going to work through by yourself for next week. Yeah, if it clashes, we can figure out a different way of doing this. Okay. Any other concerns? No, okay. Okay, so tutorial number 4, almost halfway. Some announcements. Your first problem set to do on the 6th of October. Make sure to submit it on Quarkus by then. And there's no specific template. Just make sure it's neat and legible. Some just from the last tutorial, just to sort of fix some of the explanations maybe that I confused some of you with. So with this question, it said from the same ceramic material. The same ceramic material implies that both the beams, regardless of orientation, have the same fracture strength. So if you remember, it's that stress of fracture, or we can think of it as the yield strength, or stress at which it will cause fracture. So for that case, since they're both fracturing, they will have the exact same stress. If we weren't considering fracture, then it would have to say somewhere in the question what the stress is being applied. But here, since it's the stress of fracture, that means that they have the exact same stress. So just another point, they can experience different stresses during bending, but their stress at fracture will be the exact same. The same ceramic material also implies they have the same Young's modulus. So that's just from last week. And then for this sort of extra problem, I know I sort of confused some of you with, but I was just trying to show this is the sort of plot that you would draw. And then let's say when we do plastically deform and we remove the load, we can draw this parallel line to this line here. And then we could find sort of where this plastic strain is from this point here. But this isn't really, you don't really need to know this. So that's everything from last week. Okay, moving on to this week. So some content review. Density is mass over volume. It's typically given in SI units of kilograms per meters cubed, or other conventional units like grams per meters cubed. Typical metals around you contain ordered polycrystalline structures, crystals on the micron scales. And note there are exceptions. We can have amorphous structures by creating disordered crystal structures, such as when we alloy metals. Crystal structures are made of regularly spaced atoms in repeated positions, and they're spaced at the atomic scale of 10 to the minus 10. These crystals can make up grains, sort of shown in this picture here. So this would be like a bunch of these different grain structures here. And then the boundary between grains are these grain boundaries, and that's sort of highlighted in this red. A grain can contain 10 to the 19 or 10 to the 20 atoms, so a lot. Some structures, so simple cubic is this one here. Face-centered cubic has an atom at each face. It's shown here. The cube edge length is represented with A, so that's just from the corner to corner. And the models are based on our hard sphere model from before. And then we can draw small spheres as representations, but these orientations are fractions of atoms. So that's sort of shown here. If we consider that actually putting them all into a cube, we only use a fraction of the atom. And then the coordination number in these structures is how many atoms are bonded to a single atom in the structure. A body-centered cubic has a central atom in the cube, has a coordination number of 8, so you have 8 atoms that are bonded to it. And it has a coordination, FCC has a coordination number of 12. So just going back to that, if you can sort of see it, I'll show a better diagram later. And then, so that's FCC, that's BCC. So splitting atoms into fractions can help us find densities and volumes of these crystal structures. So when we just consider all the different faces and how they intertwine with other unit cells, we want to just consider what's in our unit cell. So you have to break off sort of the part of the atom that's not contained within our cube. So let's say on this face, we take half just because that half is already outside of the unit cell. And then let's say with the corners, we're only taking that 1/8 that's in that corner, right? So this is sort of how we have to envision whatever's inside that cube. And then I'm just have a point here, try to visualize how these corners, faces, and centers all interact within a 3D space. It can be sort of tough since everything's on a 2D plane, but try to sort of see it. And we can sketch 2D relationships and use trigonometry to help formulate densities and volume relationships. So we'll see that in the upcoming slides. So this is just sort of some notes I made. So how to think of densities. Mass of atoms in a unit cell are equal to the number of atoms in the unit cell times its molar mass of an atom over Avogadro's number. So the theoretical density of a crystalline structure is then given as mass over volume, where we have sort of these moles, the atoms in the unit cell, the volume of the unit cell, and then that Avogadro's number. So rho is the density, number of atoms, the molar mass, VC is the volume of that unit cell, and Na is Avogadro's number. No, don't try to just memorize the formula, but try to understand how we can relate atoms to densities. We'll work on an example and the best way of approaching this. The atomic packing factor is the volume of the spheres over the volume of the unit cell, and it's important with these structures as sort of like when we try looking at the percentage of empty space within a unit cell. Since the unit cell is a cube whose volume is 8 cubed, we can represent this formula as this, where we have the volume of a sphere over 8 cubed. And then note for calculating APFs, consider out each face and atom. Avogadro's number is just a constant sort of to how many atoms are in per mole. So it's like a constant that was found to sort of figure out how many atoms you would have per mole of molecule. That's sort of answer. Since everything sort of, when we talk about chemistries, we put everything into moles, but since everything has a different mass, molar mass, it's just sort of like if we want to find so we're given a number of moles based on the mass in grams. So yeah, like every atom has a molar mass. We can multiply that molar mass by the moles that were given if you want to find like, let's say, just the mass in grams. And then if you want to find how many atoms, then you would use Avogadro's number. So that's sort of what the number is doing. Yeah, the mass in the periodic table is 1 mole of the element. It's just like a sort of like a unit just to keep everything sort of on that same unit. And most chemicals, when you work with them, they're given in moles. It's just like a chemistry thing instead of like atoms or something, because I would just, yeah. Uh, I'm not sure what the units are. I don't think Avogadro's number has units. It's just a constant. If you look at this, if no, but if you look at this equation here, we take the number of atoms and then we take the molar mass of the atom. So then that would be molar mass would be in grams per mole, and then the number of atoms would be your moles. So then you end up with the mass of the atom. So this would be unitless. It's purely, yeah, it's purely just a sort of like a scaling relationship that they found. Yeah. Again, we're just gonna be thinking of everything in sort of like moles, just because that's sort of how the periodic table works. Um, So finding theoretical density, some tips. So consider that the atom you're working with and its crystal structure. So example, aluminum has a face-centered cubic, and find it on the periodic table. And then we note that atomic mass in its units. So again, atomic mass is given in grams per mole. And then we find the number of atoms in the unit cell. This is N for this crystal structure. Next, we find A by considering the relationships between the atoms in the crystal structure. We set A into the VC, so the volume of the unit cell, as A cubed. And then we put it all together, and we have to be careful of units, making sure that we're using grams, everything's in grams, or if we're using kilograms, everything's in kilograms. And then we can just set it in here. And we'll go through an example later on. So atomic packing factor tips, we draw out a simple diagram of the crystal structure, like the best sketch you can do that sort of helps you visualize how it looks like. And then we find the VA of the unit cell, the amount of atoms for the volume of sphere. And then we calculate this volume of the unit cell as A cubed again. Defined A, we consider the relationship of the atoms and their spacing. And we have to utilize some trigonometry to get expressions in terms of radius. And then we can just set it in this ratio here. Again, we'll go through an example of this. So this is our first sort of example where we do an FCC APF. I have it written down somewhere. Let's see if the pen works today. Yeah, it does. So again, APF is the N atoms, the atoms, the unit cell. I'm just writing it out instead of the subscripts. So this would be your 4 pi 4/3 pi r cubed, which is volume. This would be the number of atoms. And this is your A cubed. So let's just do N. And then in order to cancel out R, we sort of have to figure out, based on this crystal structure, how A relates to R. So then we can just get some sort of percentage or ratio, right? So we sort of look at our diagram here. We have this diagonal face, or we sort of have this triangle that we can build where we have the purple atoms here, and then we just have the one in the corner. And since every face is the exact same, we only need to consider this one face, and then we can sort of just multiply it, or we can just add it into this sort of thing here. So we have to find out how this relates to R. So again, this is A, that's A. And then now we have to think about the radiuses here of each sphere. So the sphere of that corner is going to have a half, because we're only going until this corner here. And then this one too. So that's 2 halves. And then we have a full one here, so a full radius. So if you add that all up, you get 4R. Does everybody see that? So I'll just put 1/2, and then another 1/2, and then a 2. And we get 4R along the diagonal. And again, since every face is the same, we can sort of solve for A and its relationship with R. So if we just think about some trigonometry here, we use the Pythagorean theorem. We have A squared plus A squared equals 4R squared. And this is just A squared plus B squared plus C squared from trigonometry. So you get 2A squared equals 4R squared, 16R squared. And then A equals 2√2R. This is pretty sure. No. 4. Okay. So A cubed is the volume of the unit cell. And we get V unit equal to A cubed Okay, and then for our V atoms, let's see, we can just push this over here. This is our V, C is right here. V atoms. If we consider the whole unit cell, how many atoms do we have? So we have 1, 2, 3, 4, 5, 6, 7, 8 in the corners. So if we take 8 times 1/8, that's for the corners. And how exactly do we know if the atoms are touching diagonally or on the edges? Are you talking about like these center atoms of how they're touching with the other ones? Yeah, so like if you just sort of look at it from a side view almost, like if you literally just draw this square, right? And see how it sort of cuts into it. Like I don't know, like for this radius here, we're just purely looking at how it interacts with this square here. So since we only can go halfway through the circle to get to the corner, we only consider half. But since this line is literally going through the whole of this sphere in the middle, then we use the whole radius here. I'll do an example with the other case where it's a little different for BCC. But yeah, just I would say like literally just cut that sphere to fit into that unit cell. I think that's the best way you can do it. Yeah, like if you yeah, you gotta visualize or you can try sketching. I'm not very good at like drawing these types of things, so I don't know if it would just confuse you more, but like you just imagine like let's say even that top here, like let's say we just cut everything so it would fit into this thing, like this would all be halves, right? Yeah. It does get like kind of tricky, but at least like I feel like you're not gonna be doing too many of these crystal structures. You're only gonna be learning about some. So just knowing how to visualize these more basic ones is usually, a good step forward. So again, so our V atoms, let's say just based off of let's say this comment, make that big. It can be hard. I feel like the relationship with A is tricky. And then also just visualizing the amount of atoms sometimes can be tricky. So again, we just have to cut everything. So these corners, if we have sort of something like this and we have this sphere, these corners, we can only take the sphere that interacts with here. This part, and this part. Let's say how it makes this sphere. These pieces here we can't take. So we get 1/8 of the whole sphere in the corners. And then if you consider these faces here from a side view, this is sort of the face atom here. Everything that's shaded here is within our unit cell, but this is sticking out. So we can only take half of that. So on each face, we take a half. Since we have 6 faces, we get 6 halves. If you add this up, you get 4 atoms total. So then, based off of this relationship, our APF is equal to 4 atoms times 4/3 pi r cubed. And then we have our A cubed. So we get 16/3 pi r cubed. And then we just expand this, we get 8 to the root 2 r cubed. And so this is 16 here. So this 16 and that 16 cancel. And then we get, and this r cubed and that r cubed canceled. So we get pi over 3 root 2, just because this comes down. And If you plug that into a calculator, you get 0.74. And if you wanted a percentage of like sort of how much it takes up the space, you just multiply that by 100%, and you get 74%. So that's FCC. And then next we do BCC. You like BCC is a little trickier when it comes to finding A, but it might be easier for visualizing how to get the total atoms. So again, we have APF. Yeah, this is the one where we use diagonals. Yeah. And this is the only reason we use the diagonals is because you do have that center atom, so you can't consider just the faces anymore. The other one, since everything was identical, every single face, you don't have to consider the empty space in the middle, let's say, right? But here, since we have this atom in the middle, you have to consider how that center atom relates to all the faces. So that's sort of where you're building this diagonal relationship. Yeah. So anytime you have some sort of atom inside your space in the center, you have to relate that atom to everything else. And then you can just use symmetry after the sort of, yeah, once you have that relationship. So again, we start with, and what's horrible. Let's do, and BC. So our start with finding this, and so we just consider how many atoms we have. We have a whole atom in the center. Well, that's where we get 1. And then we have 8 atoms on the corners. And remember, the corners are 1/8. So this gives you 2 atoms per unit cell. So that one's a little easier for finding the number of atoms. But then finding the V unit is a little trickier, but we'll work through it. So I like this diagram because it shows different colors for sort of what we're trying to relate. So the first relationship, we're considering how every face interacts with sort of the center atom. And that's represented by the blue, green, and red here. So we sort of build this diagonal with the blue, green, and red. We have this, 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 and this. And this is blue here. Maybe I can just change the color. So this would be blue. That's red. And this is green. And then we just consider the relationship that's on the bottom here. It can also be the top or any other sort of diagonal that you can see. So again, we take red, red, and then we have blue. And the reason why we choose this diagonal here is because you're going to get a relationship in terms of a diameter here. And since we're going to have 2 variables, we need 2 equations to sort of cancel out one of those variables, right? So we only solve in terms of 1 variable. So that's the only reason why you need 2 triangles here. If we're able to sort of make that one triangle in terms of 1 variable, then it would be easy, right? So remember, the reds are A. That's our typical unit cell radius. sort of. And then we have a diameter. And we have 4R. So again, if we consider just half to get to this corner, a full and a half. This is the diameter. So blue is diameter, green is your 4R, and red is your A. And since we have two triangles, we can sort of use Pythagorean theorem. So we get A squared plus D squared equals 4R squared. And then we have A squared plus A squared. Actually, I'll put that here. D squared. Then based on this, we can put D in terms of A. We get D squared equals 2A squared. And then we can put that in there. So we get A squared plus 2A squared equals 4R squared. That's sort of how we use that other triangle to sort of get it all in terms of one. And from this, we can get A equals 4 over root 3R. And then we just plug this into our APF relationship. So we have 2 atoms from earlier times 4 over 3 pi r cubed over 4 over root 3 r cubed. And then this is root 3 pi over 8. And that is equal to 0.68. And then we can multiply that by 100 if we want it in percent. We get 68%. Again, so just to reiterate, we sort of use the second triangle because you have this second variable. And the only reason you have this second variable is because if you look at that diagonal, you only have these 2 atoms in the corners, but there's nothing in the center. So you don't really have anything to relate A to sort of how long this length is, right? So you sort of end up with an unknown. Okay, I'll continue. Unless there's some questions about that. I know that one's a little trickier. So just sort of how crystal structure may affect something. So the atomic arrangement can affect the density, strength, and electrical conductivity. So metals tend to have tightly packed structures leading to high density and good conductivity. It's easy for sort of charge to flow through these structures. The lattice structures with more densely packed planes allow for more plastic deformation compared to loosely packed. So if you sort of think of when we cleave something, the structure, if it's really dense, sort of will shift and it can't go back, while loosely packed sort of it has that empty space for movement, right? And then surface characteristics, each face of the crystal intersects at specific characteristic angles. So we can use X-rays to analyze these unique patterns to identify materials. So there's something inherent to sort of like the chemistries and their crystal structures. And then crystal habit, visible external shape determined by the crystal structure, chemistry, bonding, and formation conditions. So this is a mineral right here, pyrite. And it has it has a simple cubic structure, and we can see that it literally forms on the macroscopic scale a simple cubic structure, which is really nice. And then this one in the corner, I don't know why the animation stopped, but this is diamond. Diamond has a it has a type of face-centered cubic that has like atoms within also. But you can sort of see that it also has some sort of crystal structure that can kind of represent like how you see a diamond in the real world, but this is more just for like the you can see how dense it is, and that's why it has so much strength as well, right? And then so I just have a little exercise. Can you think of no, I don't think so. This is just for an example, so you can sort of see how different materials that you see in your day to day, how their crystal structures can sort of look like. Can you think of other examples? And then just you guys can take 5 minutes to research some sort of crystal structure of a material you know, and then just I don't know, put a name of something you know and what type of crystal structure in the chat if you find something. Sorry, give until 1:57. And if you can't find something, that's fine. It might be tough. Yeah, what kind of structure does gold have? Uh, let's see. Yeah, it has a typical face-centered cubic. Uh, yeah, every like a lot of the metals, yeah, will have a crystal structure. Some will have something that are unique, and then others will have something that's more common, right? Like, let's say even if you consider diamond, right, that's still considered a face-centered cubic, is just it's its own iteration of a face-centered cubic, right? A lot of cool sort of crystal structures. Yeah, there are exceptions. There's a lot of exceptions. Usually like metallic elements have more common stuff, but then when you get into like trickier sort of elements then or combinations of a lot of elements, then you get like really these hybridized crystal structures. So again, pyrite is it's a mineral, so it has a bunch of different metals in it. So if you look at a lot of different like actual minerals or crystals, they might have a whole arrangement of metals, so they can form like really cool structures that you probably won't see commonly that are unique to like that single one. Bismuth. Bismuth. Yeah, so bismuth has something that's unique, right? as a sort of like triangular stacked, right? So you're find out like if you go into sort of like this materials, or let's say you in your later years when you sort of take courses in these types of materials things, you see that you can get these really unique crystal structures, and you can dope and change electrical conductivity and things like that. So yeah, it's really nice outside. I probably should have stayed outside, but I was scared that the Wi-Fi might go out.
I couldn't run back to the library in time, so I'm at Part House.
Well, I would say if you can, then enjoy the weather outside, because when are you gonna get 30-degree weather in October? Um, I'll just continue. So this is sort of going into more unique stuff here. I guess this would be like the first unique thing based on the rock salt structure. So your typical sodium chloride salt. So here we take the empty space and we sort of plug in, we have these cations and ions intertwined within an FCC structure. So then you have a lot more space taken up. And then we just make sure that these stoichiometries always line up. So we end up with a 1-to-1. So when you're working with sort of these more complex anion cation structures, just make sure that whatever your ratios here line up with whatever's in the unit cell. And then, so this 1-to-1, so there should be 4 total atoms if you look at all the pieces within the unit cell of each. And as ceramic crystal cations will always touch their anion neighbors. So you can't really see it here, but if you think of this as a large sphere, these would actually be touching. And then the theoretical density for ceramics is given by this sort of ratio here. So it's just the sort of distribution of anions and cations. And we just have to be careful to calculate the lattice parameter A by using both the cation and anion radii. And then the cation coordination number for rock salt is 6, as it touches 6 neighboring anions. So that's sort of shown this corner here. So 1 anion to 6 cations, or 1 cation to 6 anions. Interstitial sites are spaces found in between atoms. So that's sort of these gaps here. The space may contain another atom. Is it different online that they put the anion somewhere else? Because technically, like, you could just shift your crystal. Oh, are you just asking in general? I'm not sure, to be honest, but if you shifted your structure, you could technically have the cations on the corners, right? As long as there's a 1-to-1 ratio, I don't think it should affect any calculations, even if you switch them. Because if you think of just how, if you haven't, like, if you just think of if you had like a bunch of these unit cells connected, right? Even if like you just considered a shifted unit cell to the left, let's say by 1 atom, right? You'd still end up with the same stoichiometry, and technically it would still be touching the same amount because you'd have an infinite amount of these unit cells around it, right? So as long as it's symmetrical, I don't think anything would change. I think for this purpose, I think that was just his preference. Yeah, you gotta make sure that in the unit cell, everything's the same. And again, it's if it's symmetrical, right? Like in this case, if you consider like 100 of these unit cells beside each other, they're all gonna sort of be spaced the exact same way, right? So even if you took one that was slightly to the left or one that was slightly to the right and it had, one had cations on the corners, one had anions on the corners, like you're still gonna get the exact same sort of calculation in that unit cell that you choose, right? But if you chose something where, you know, the unit cell has different things inside as you look, then that's a different story, right? But here everything's symmetrical, so even if you just shifted it by one unit, yeah, it would still be the same. Again, stoichiometry is really important. So interstitial sites are the spaces found in between atoms. This space may contain another atom, such as a cation in the space of anions, or it can be empty, similar to the positions in the FCC metallic structure. So that sort of, you can see how the cations and anions, how the anions take up the space, or the cations take up the space. We name interstitial sites by the solid geometry that they create. So if you think of when this was empty, there'd be sort of a hole here. But since we did add something, now we sort of have these shapes that are sort of made. And then the interstitial site with coordination number 6 is an octahedral interstitial site. This is the rock salt interstitial site. It is named octahedral as it contains 6 faces to form an octahedron. So I think that one's a little easier to see, but I would say the simple cubic interstitial site's a little harder. So a simple cubic has an interstitial site coordination number of 8, and it can be thought of as a spatially similar to a BCC structure where the cation in the middle touches each of the corner anions. So if we just think of this as simple cubic and then we just add a cation in the middle, now we get sort of like a BCC structure. And so it changes sort of that coordination number. And then the middle touches each of the corner anions. And this interstitial site has 8 faces, that's giving it its coordination number. And then to sort of visualize this, think of 2 upside down pyramids connecting at their vertex. So I sort of try to highlight this. So you have the face. This is sort of how I visualize it. You have this face here, this face here. Then you have the back face there. Then you have a side face here. And they all connect. So this all connects here. So there's your one pyramid in blue. Then you get sort of a reflected pyramid on the other side. So like that. And this pyramid has 4 up here, and then this has 4 down here. And that's why you get 8 faces, and that's why you have a coordination number of 8. I think that's how I sort of see it. Does everybody get that one, or? Okay, good. Okay, so we have a quiz. How I'm gonna do the quiz this time is I'll probably just share the document, and then you could just do all the questions at once. It'd be a little easier that way. So I'm just gonna stop sharing for now. This quiz I think is mostly like multiple choice. Perfect. Okay. I'll share it. I'll give 15 minutes. Should be enough time. Everybody see that? So yeah, 7 questions. 15 minutes, so I guess starting now. No, it's not graded, don't worry. This is just for practice. Yeah, whatever you prefer, but yeah, in terms of a ratio. It was in terms of percent, like the question would ask for a percentage. I'll take up the answers and right now. Okay. Go back to the presentation. Oh, that's the answers there. Any questions with that? These bottom like 4 to 7 we covered earlier, but I can show the coordination number again. That's the next slide. But anything with 1 to 3?
For number one, is for D, is it the word completely that's like the main word that makes it wrong? Or
For number 1?
yeah, for D, is it the word completely or is it
Uh, yeah, because it's like there could be, it's usually just like it's a bunch of ordered crystal structures mixed in with each other, right? So there's still some sort of, there is positions of atoms. It's not completely random. Yeah, it's just, it's more of like a mix of positions, right? So like let's say if we take like an FCC and we mix it with a BCC, there's still, there could be a percentage of, let's say 40% FCC, 60% BCC, but there's still positions, right? It's just now you have an amorphous because you're mixing two things, right? So can you explain why C is wrong for 1? It is true. Like polymers tend to be fully ordered. Like usually they have some sort of like linear chain, or they could be like they could build like mesh networks or something. But there's a such thing as semi-crystalline polymers. Um, I can explain it later. I can pull up like a diagram or something. But there are like certain semi-crystalline polymers. Everybody's good with 2 and 3 though. Or just show sort of how we get coordination number for these ones. So that's how you sort of see it. And I'll just yeah. Like amorphous just means like a mixed structure, right? But it doesn't technically necessarily mean that it's a randomized structure, right? Like I can also pull, yeah, I can make a note of that, and after we finish with this stuff I can talk sort of about semi-crystalline. I could talk about amorphous, and then I can talk about something else that I was sort of thinking about. So I'll just do some sample, like two quick sample problems, um, based sort of on what we learned. And today, I don't know if I'm gonna do the whiteboard just because these answers are like pretty long, so I'm just gonna try explaining it as best as I can instead. So when we think of this sort of theoretical density, we go back to slide 9. So we sort of have this theoretical density of a crystalline structure is given by this relationship. So if we just think of density, density is given as mass over volume. Then we get number of atoms with molar mass over the volume of the unit cell, and then Avogadro's number. And then, so usually we can find that aluminum is FCC. So that gives us that N equals 4 atoms. If we remember from here, if we just look at that unit cell, each corner 1/8, and then each face 1/2. So 6 1/2, 8 1/8 gives 4. And then the atomic mass A of aluminum is given as 26.982 grams per mole. And then I'm gonna talk about this later, but here's this Avogadro's number again. And I said earlier that it's not, it doesn't have units, but it does. But it's, again, it's a more of a dimensional number than it is, really affecting anything. It's purely just to make sure your dimensions are right. It's like a scaling factor. And then I'll do an example to show you what it means. Since the unit cell is cubic, the volume is simply cubic of its sides. So we get VC is A cubed as before. We can estimate A from the radius are of the atoms in the unit cell. And then, so FCC, the atoms touch across the diagonal on a face. So from earlier in the tutorial, you should remember how we calculated it, but we got that A is 2 root 2 R. Now if we put this together and we just consider the units, so put together, consider units. So we have A in grams per mole and R in meters. Calculated density will be in grams per centimeter cubed. We're just to plug in based off of that relationship. So we get this for atoms. That's our N times 26.982 grams per mole over 2 root 2. And then our R is 3 times 10 to the minus 9. And then I think this is in centimeters. Okay. I think this number you can just Google, but usually it'll be given. And then so this cancels with that. And this, we're left with grams per centimeter cubed. So you should get 2.7 times 10 to the 6 grams per centimeter cubed. And that would be your theoretical density of aluminum. So that's sort of how you would find a theoretical density.
That feels a little high, doesn't it? It's very
Sorry?
like 2.7 to the power 6 grams. Is that right?
It's in grams per centimeter cubed.
Yeah.
Um,
So it'd be
well,
like 7 kilograms per cubic centimeter.
yeah, it does seem a little high. Well, again, this is like just the theoretical, right? It's probably different than, real world stuff compared to theoretical. That's why you have these types of jumps. But this is just sort of like the example of you had an ideal sort of again, the aluminum we use in the real world is different than like pure aluminum, right? Oh, sorry. That's fine. That's in meters. I don't know why it's. Is that a little more realistic now?
Not gonna lie, it feels a bit too low now, but oh well, it's okay.
Yeah. Again, it's theoretical. It's like you're gonna have some different stuff in the real world, but that's just sort of how you do a calculation like that, based off of what we're given and what we've learned in class. The next problems would demonstrate that the ideal cation to anion radius ratio, RC over RA, in the rock salt structure, that is a cation that just fits into the octahedral site without pushing the anions apart, is 0.414. So this is sort of our rock salt structure. How should we start this calculation? So if we just consider one cation, so the cation in the middle, so the very center one, let's say this one. The unit cell touches 6 anions. So 1, 2, 3, 4, and then 6. Yeah. The middle of the faces. It has coordination number 6. We showed that before. Not being pushed apart. Then they touch as well. So a sketch of the of a plane centered around a cation would look like this. So let's draw it. So actually let's use, so this is our cation. And then these would be our anions. So if we just drew like a square that was perfectly symmetrical, we have A would be our one side length here. But if we actually consider the radius is of our anion, we can actually see that maybe I didn't draw this the best, but these were all the same size. Then we can see that A is equal to 2RA. And what I'm trying to show here is that we get 1/2 from here in the unit cell and 1/2 from here in the unit cell. So you get 1/2 RA from that one, or no, you get 1 radius from this one. You get 1 radius from that one. So you get 2 RA. And then if we consider the diagonal, you can see that we get a radius from this one, a diameter from the red, and then a radius from, yeah, when you consider all these sort of these structures, we only use the small spheres just to show like as a representation. But like what's actually happening is like they're actually like really close, sort of what this sketch is showing here. So like when you think about our atomic packing factors, if like let's say 74%, right? Like this one has like much higher, right? And it's, if you think of like that atomic packing factor, that's the empty space within a unit cell. And if it's 74% is taken up by atoms, then you know, your spaces would literally be like something like that, right? Like they're all like very close to each other. It's just for these sketches here, is just to represent sort of so you can actually see what a unit cell would look like. But they're actually a lot bigger, right? Yeah, so if we consider from this point here in the unit cell, that's 1 radius from this one. So we get 1 RA. Then from this one, we get 1 RA. And then from this red here, we get a diameter, which is just, so we get 1 diameter of the cation, which is just equal to 2 radius of cation. So if we consider this diagonal length, the diagonal length is just 2 RA plus 2 RC. So we can use slide based off of that sketch. You can build triangle where this is that diagonal. See? And then we have 2 RA and 2 RA. Again, maybe I can, I don't think I can move it. But basically, again, so we have A here, and this A is 2 RA. I don't know why I put A twice. 2 RA. Then we have 2 RA there, and then we have that diagonal. So we're building this triangle here, let's say. So we consider some trigonometry. We have sine theta equals opposite over hypotenuse. So since this is a cube, right? These triangles would have 90 degrees, so these would be 45, right? Perfect cube. So that implies that sine of 45 degrees is equal to 2RA over okay. And then we just gotta isolate RC over RA. So we get RA sine of 45 plus RC RA over RA sine 45, RC over RA sine 45 equals RA over RA. So that's one. That's one. And then we get RC over RA. 1 minus sine 45 over sine 45. And that's equal to 0.414. And you can just expand this if it's easier to see. So and then we just and that's how we get there. Everybody good with that? Okay. So that's sort of how you would tackle something like that, right? So that's it for content. I'll go through a couple extra things just based off of some discussion we had today, but that's it for I guess what I'm gonna record. So